This time talking about how flux can be used to solve real problems, and something called Gauss's Law, which allows us to calculate quite easily how much flux to expect. We've seen before that with a gravitational field, the total amount of flux emerging from a mass of m1 is 4 pi g m1. And we can do a very similar calculation for electric fields. We know that the electric field strength, that's just the force on a unit charge, is Q1 over 4 pi epsilon naught r squared. Comes directly from Coulomb's law. That's the force due to a charge Q1, a distance r squared away from a unit charge. We know that the flux density is equal to the field strength. So this is the flux density. Now the flux density is the flux divided by the area. So consider a charge Q1 at the center of a sphere of radius r. Now, by symmetry, the flux density must be the same everywhere on the surface of the sphere, because everywhere on the surface of the sphere is the same distance r away from the charge Q1. So the flux density is the total flux divided by the surface area of this sphere. But that must be equal to the field strength. So we get that the flux over 4 pi r squared is equal to Q1 over 4 pi r squared times epsilon naught. The 4 pi r squareds cancel. Net result, the total flux emerging from this charge Q1 is Q1 divided by epsilon naught. And it's generally true. The flux emerging from a charge of Q is Q over epsilon naught. And this is what Gauss's law tells us. Now, we can apply that to some interesting situations. First of all, this one. This is a plate of uniform charge. It's an infinite plate. It goes off to infinity in all directions. That's a difficult thing to draw on a piece of paper, so just use your imagination and assume that this is an infinite plate going off to all directions. It has a uniform charge density. The charge density is measured in coulombs per meter squared. I'll call it rho. And that's the charge in a unit area. So, if I took a small area here of, say, delta A, the charge in that small area delta A would be rho times delta A. Now, what would the field strength be a distance, say, d above this infinite plate of charge? Well, first thing we can do is work out in what direction the field would be at that point there. I can draw any line at all through that point and look at the effect of all of the charges on this side of the line. They will be trying to push a unit charge there in that direction. All the positive charges on this side of the line would be trying to push the unit charge in that direction. Since it's an infinite plate, there will be exactly the same amount of charge on this side as there is on this side, with the net result that the horizontal components of these two forces will cancel out, leaving a single force going straight up. That tells us that the direction of the field strength at this point here is directly away from the plate. But how about the magnitude of the field strength? Well, to work that out, we have to introduce the concept of the Gaussian pillbox. The Gaussian pillbox is a narrow cylinder which goes perpendicular to this infinite plane of charge. And it has a cross-sectional area of delta A, which means the charge enclosed in the Gaussian pillbox is rho times delta A. Therefore, the flux that's emerging from this Gaussian pillbox must be rho delta A, the charge, divided by epsilon naught. That's what Gauss's law tells us. We know that the direction of the force is directly away from the plate, so the direction of the flux lines must be directly away from the plate as well. The flux lines, due to the charge in this pillbox, can go in two directions. Half of them will go straight up, and half of them will go straight down. So the flux emerging from the top of this plate here, the flux coming out, would be the total flux emerging from the Gaussian pillbox, rho delta A over epsilon naught, divided by 2, because half of it is coming out the bottom of the pillbox. The flux density emerging from the top is then the total flux emerging from the top, which is rho times delta A over 2 epsilon naught, divided by the area, delta A. So the two delta A's would cancel. That gives me that the flux density is rho over 2 epsilon naught. But the flux density is equal to the field strength. So, we have now worked out what the field strength is at distance d above this infinite plate of charge. It's rho, where rho is the charge density of the plate, divided by 2 epsilon naught. The interesting thing about that is that it's not a function of d. It doesn't matter how far you are away from this infinite plate, you would experience the same field strength, and therefore the same force on any charge that happened to be there. It's only a function of the charge density and the constants. Next time, we'll be applying this result to the parallel plate capacitor.